In the previous video, we learned about the formula. Initial value increased by some percent would give us final value. What you see here in brackets stands for 100% plus that rate of increase. Using this formula, we can find the formula for R. To do so, we'll divide both sides of this equation by VI, and we'll obtain that 1 plus R equals to VF divided by VI. From here, we'll find R, which is VF divided by VI minus 1. And from here, if we find the common denominator, it will be VF minus VI divided by VI. If I now write this formula here, it will be R equals to VF minus VI divided by VI. So final value minus initial value divided by initial value. Of course, the answer that this formula will give will be in terms of a rate per one. And if we want to state this formula in terms of percent increase, it will be R percent equals to VF minus VI divided by VI times 100. That's because in order to convert rate per one into percent, we need to multiply by 100. An important note is that we found this formula for percent increase, but actually it can be used for percent decrease as well. It's just the result will be negative for percent decrease. That's because final value minus initial value will give negative result if it is a percent decrease. For example, how can we use this formula? Let's see this problem. $450 has declined to $412. What is the percent of change? The formula for percent change in terms of rate per one is this. Final value minus initial value divided by initial value. So rate per one for percent change will be your final value, which is 412. That's because the investment has become $412 minus initial value, which is 450. That's because investment started from the value of 450, and we'll divide that by that initial value, which is 450. The result is minus 0.0844, which is minus 8.44% rounded to 2 decimals. This is the solution, and negative sign here shows that we're talking here about percent decrease. Because we use this universal formula, which initially was obtained from percent increase, the negative result means that we're talking here about 8.44% decrease. Now let's speak about average percent of change. This is going to be a little bit more complicated. We start with an initial value VI, which has been increased by some percent. Let's say then this increased VI has been increased again by some another percent R2. And then let's say it was increased again by some percent R3. And that gave us the final value. So in this case, we increased VI 3 times. First by some percent, then by another percent, and then by another percent. All that gave us a final value, which is the ultimate final value. You need to realize that actually there are 3 final values here involved, right? So the first final value is after the first increase, then the second final value, and then the third final value, which we now call this VF. Let's consider now the following situation. I take the same initial value and I increase this initial value by some percent. Then I increase the resulting value by the same percent, and again I will increase the resulting value by the same percent in order to get to the same final value. Of course, all these three brackets will result in an exponent, so it's multiplication of the same number. It will be vi, 1 plus r, exponent 3 will be vf. If we now compare what I have done here with three different increases with what is written here, which involves the same percent increase 3 times, we can pose a question. How can we find this r, which if applied 3 times, will give us the same result as 3 different increases? So based on these two equations, I can write that 1 plus r exponent 3 should be equal to 1 plus r1, 1 plus r2, and 1 plus r3. From here, we can be solving this in the following way. 1 plus r equals to 1 plus r1, 1 plus r2, 1 plus r3, and I'll take exponent 1 over 3 here. I can remind that the reason we did this is because when we solve an equation such as x exponent 3 equals to, let's say, 8, the way we solve it is by finding reciprocal exponent on both sides. So in this case, x is going to be 8, 1 over 3. This gives us 2. So we did the same process here. We found reciprocal exponent to 3. This allows us to find r from here. And that will be 1 plus r1, 1 plus r2, 1 plus r3. All that is exponent 1 over 3 minus 1. So we move this 1 to the right side. What we see here is the formula for so-called average percent of change. The way we constructed this formula shows that if we have a process such that we have 3 sequential changes of different magnitude, we can ask a question: what one change applied 3 times will give us the same result as those 3 different sequential changes? And this formula gives us that average percent of change. It is highly important not to mix up this average percent of change, which is actually also is called in mathematics as geometric average, with arithmetic average. So one should not confuse this type of average when you take these 3 increases and divide by 3. So if you do that, this will give you arithmetic average. Which does not have the same meaning as the one we are going after in this exploration. To clarify this, let's have a simple example. $1,000 increased by 50% and then by 30%. So what is the average percent of increase? If we take arithmetic average, it seems like we should solve this problem as this. 50 plus 30 divided by 2, which would give us 80 divided by 2, 40%. Let's try now to apply this 40% increase 2 times. So we'll start with $1,000 and apply 40% 2 times. 1,960. So is this the same final value I could get by applying 50% and then 30%? Let's see. If we take the same $1,000 and apply 50% and then we apply 30%, the result would be 1,950. as you can see, we don't have these values equal. Therefore, this process did not give us the correct average percent of increase. What we needed to have was that $1,000 had to be increased by the same rate 2 times in order to get to 1,950. And this R can be found now in this problem, of course, using this $1,000 and 1,950 by 1 plus R squared equals to 1,950 divided by 1,000. And from here we can find R, which is 1,950 divided by 1,000, 1 over 2 minus 1. 39.64% rounded to 2 decimals. If we use our formula that we obtained earlier, this one, we could also solve this problem without invoking initial value and final value. So we could use that formula, which is 1 plus 0.5, 1 plus 0.3, 1 over 2 minus 1, which is going to have the same answer, 39.64%. This example demonstrates the difference between arithmetic average, this one, which is incorrect for finding average percent of increase, and the geometric average, which is found in this way, using the formula that we obtained here. Therefore, when we solve for average percent of change, we're not going to use the arithmetic average. Instead, we'll be focusing on geometric average. For this reason, we'll be writing subscript G here. Of course, this formula can be extended in obvious way to any number of different changes, increases or decreases. If you want to find average percent of change, so this geometric average, when multiple various changes are involved, so you will use this general formula. So there will be multiplication of any number of brackets, exponent 1 over n minus 1. This formula gives us that change, which if applied n times, will give us the same result as n different changes applied one after another. Here is an example to demonstrate once again the application of the formulas we spoke about today. A stock has grown over the last 3 days in the following way: 4% increase, 7% increase, and 5% decrease. What is the average percent of change and what is the overall percent of change? We'll start with finding average percent of change. This is going to be the geometric average, Rg, which will equal to 1 plus 0.04, 1 plus 0.07, 1 minus 0.05. The exponent in this case will be 1 over 3 minus 1. 1.87%. Because we have here positive sign, it means that we have 1.87% increase. The meaning here is that the stock on average increased by 1.87% per day for 3 days. What is the overall percent change? We don't know the initial value here, but we can investigate what happens for each $1 of the initial value. So each dollar has grown at 4% first, then it has grown at 7%, and then it declined by 5%, which will give us 1.05716. By the way, in this problem we are not told the actual sequence of how these increases and decreases happened. For example, 5% decrease could happen first, and then 4% increase, and then 7% increase. But because of the commutative law, we don't care about the actual sequence. Commutative law means that A times B is the same as B times A, for example. And that's true for any kind of number of terms. So A times B times C is the same as C times B times A, for example. It doesn't matter in which sequence these changes happened, because I can simply change brackets here. Let's return to this solution. $1 after all these three changes has become 1.05716. Of course, from here I can see right away that the total percent change was 5.716%. But to have a practice with the formulas, that of course is evident from the formula that we had for percent of change. Final value is 1.05716 minus 1 divided by 1. Of course, that results in the same answer. Here we go. In this problem, the average percent of change is 1.87%, and total percent of change is 5.716%.